I like counting. I like continually multiplying things by 2, although by the time I got to 1024 or whatever it is, I had enough of it. But I like math. I discovered as a very young kid, maybe 4, something called Zeno's paradox. Did you ever hear of Zeno's paradox? My father told me that the car could run out of gas. And I was disturbed by that notion. It never occurred to me. But then I thought, well, it shouldn't run out. It could always use half of what it has, and then it could use half of that, and then half of that, and it could go on forever, and so it would never run out. So now, it didn't occur to me, yes, but it wouldn't get very far either. But the idea that, in principle, you didn't have to run out of gas was kind of a profound thought for a very little boy.
Were you a talented student? Were you always getting really good grades in
Well, I was a pretty talented student. I knew I was very smart somehow. On the other hand, I was very careless. So I sometimes screw up arithmetic tests just because I did it too fast or sloppily. But I liked everything about it. I liked everything about math. I loved learning the formulas for the volume of a sphere, 4/3 pi r cubed. I always thought that was a great formula. When I got to high school, we started with, plane geometry, proofs and theorems. That's where I really got gripped. I really loved that. I loved working on. Some of the problems were harder than others, and I liked doing that. I was never the fastest guy in the world, but I would plod through it, and with determination. I just liked it.
Did it feel like this was where your career was going to take you, or were you like another boy who dreamed of being a baseballer or something?
Oh, no. The only thing I thought about was I would be a mathematician, whatever exactly that meant. I didn't know quite what it meant, except that mathematics was the only subject I really liked. Science was okay, but it wasn't very well taught where I went to high school. At least I don't think so. And history, English. I loved to read, but I wasn't a good writer. I read a lot. When I went to MIT, I majored in mathematics, of course, and skipped the first year because I'd had some of those courses in high school. And I even took a graduate course in my freshman year of a second semester in math, because it said no prerequisites required. So I said, oh, no prerequisites, I'll take that course. Had a very hard time getting my arms around that course. I finished it okay, but I was very puzzled by some of the concepts. However, that summer, I got another book. I got a book on, this was algebra, but not algebra like solving equations. It was abstract algebra. And then in a week, everything came together for me. I understood, I was no longer puzzled. I understood why they did everything. Other parts of math got me stymied for a while, but typically it would take some time for me to sort of grasp what they were trying to do, and then it would go very smoothly. So I graduated early from MIT in 3 years.
Did you imagine you would be a professor sitting in a university, or like what? You had no grasp of what?
I didn't. Yeah, by the time that my freshman year was over, I kind of realized that's what it would mean, that someone would pay you for thinking about mathematics and creating mathematics. What I thought earlier was I would do something that involved mathematics, but it was mathematics that I wanted to major in, and I could see quickly that, well, that's the way. If you're going to do that, you're going to be a professor somewhere and profess.
You also talked about this week of algebra where everything sort of fell into place.
Yeah.
Is that a common thing? Is this a thing that always happens? There's this moment where all the cogs move into place and it's like, oh, I get it now.
I think, yeah, there are moments like that. Sometimes you're introduced to a new concept and you wonder, well, why are they talking about this? Why is this concept interesting? And then you think and you see some examples, and they say, oh yeah, okay, this is really good. A lot in mathematics is making definitions. You'll see things that really could come together under one aegis, and you can define this set of notions, and sometimes just a structure which follows all these notions. And that's a great way that mathematics has advanced, because when you put a lot of things together that have similar characteristics, then you can try to prove theorems about the general set of things rather than some particular example. And that turns out to be a very powerful approach. So making a good definition is a good thing. They wanted me to go to Berkeley and get away from MIT, meet some new faculty, because I was quite close to the MIT faculty, and they thought, I think they didn't want to get rid of me so much as they thought I was probably pretty good, so I should get exposed to a certain guy named Chern, who was just coming to Berkeley that year. And I got this very nice fellowship, and I went there. I was very eager to work with Chern, meet Chern, except he wasn't there. He celebrated his first year at Berkeley. He had just come to Berkeley, and he celebrated that first year by taking a sabbatical. So he wasn't there. So I worked with another guy, which was fine. And by the time Chern came, in the second year, I was already pretty far along with the thesis project. I was giving a seminar at the beginning of my second year at Berkeley, and in walked this tall Chinese guy. And I said to the guy next to me, "Who's that?" I said, "Oh, that's Chern." I said, "That's Chern?" I didn't know he was Chinese. I thought Chern was probably short for Chernowski or something, or he was probably some Polish guy who had shortened his name to Chern. If it had been Chen or Chan, I would have known it was Chinese, but Chern with the R, I didn't know. But anyway, so I met Chern then, and we became friends. Of course, I was much younger than he, but we became friends, and later collaborators.
Can you give some idea about what your area of specialization is at this point? What are you zeroing in mathematically on?
Well, at that point, and pretty much thereafter, the field that I worked in was called differential geometry. And differential geometry is geometry, but it's the geometry of curved spaces. It's not flat things in the plane. It's any shape or form, but typically with some distance function so that you knew how far apart things were. And the basic object to study is what's called a manifold. And a manifold is a lot of pieces of space glued together. So, for example, the surface of a sphere is a manifold. Now, you can't just take one little sheet of paper and make a sphere out of that, but you could glue a bunch of pieces of paper together and make a sphere. So a manifold is something that locally in your neighborhood looks like it's just regular space. Maybe it's curved a little bit, but globally it could be quite different. So, and the surface of a tire, of a donut, for example, is fundamentally different from the surface of a sphere. You can't deform one into the other. What really got me onto it is a certain theorem which is called Stokes' theorem. Now, Stokes' theorem is the ultimate, I think, generalization of what was originally called the fundamental theorem of calculus. Now, I don't know if you studied calculus, but the basic theorem is if you integrate the derivative of a function, so you take a function, you take its derivative, first derivative, and then you integrate that, let's say, from A to B. Well, that gets you back the original function. The answer, when you integrate the derivative, is of f. It's f of b minus f of a. That's the answer. If you integrate the derivative of a function, you get back the value of the function. Well, that was the fundamental theorem of calculus. Presumably Newton knew that. Now, that had been generalized into higher dimensions, so there were other things you could integrate and differentiate and go from boundaries to interiors and so on. And the general statement of that theorem was to me, almost breathtaking. It was so beautiful, that theorem. And that's one of the basic theorems in differential geometry. And it's about integrating something over the boundary, and that's the same as integrating something else over the interior, something related to it. It's derivative in effect. It's differential. So there's a whole calculus of things called differential forms and integration and all of that, and that it takes place in manifolds in general, and anything that looks like pieces of space. So I love that theorem, and that's what got me into differential geometry.
So was it a beauty or an elegance you saw, or was it a trophy and a prize you saw that could be chased?
No, it was just the beauty. It was just the beauty of it. I just liked it. I had learned a fair amount of algebra, and that was fine, but it didn't grab me. But the geometry did. So that's what I specialized in. And when I got to Berkeley, I was fooling around and started. I'd made some observations, and I mentioned them to my thesis advisor, the guy I was going to work with. And he said, "Oh, that's interesting. That makes me think about such and such a problem." There was a problem floating around that people had been trying and failing to solve. But I thought, oh, that's very interesting. So I started working on that. And he advised me not to, because so-and-so had tried it and someone else had tried it, and those were big shots, and I was just a little shot. But I didn't pay much attention to him. And I solved it. And just worked through it, and you know, had a little help along the way for people, but basically I drove that. I had done some other mathematics after my thesis, work on something called minimal varieties, and it was kind of a fundamental paper. It took me 6 years to write that paper. People were, I think, thought, how could take 6 years? But anyway, it did, and that turned out to be a very good paper. That was where I was coming from. At roughly that time frame, or a year or two afterwards, I went, when I was 30, to Stony Brook to be chair of their math department. Stony Brook University was a very new university. They had a rather poor math department. In fact, it was very bad, but an excellent physics department. They offered me this job as being chairman, and I thought that would be a lot of fun. In that time frame, I had decided to try to learn something about an area of topology which is related to geometry. It's kind of handmaidens of each other, called characteristic classes, whatever that might be. And I thought, I'm going to just learn these characteristic classes because I didn't really know it, and it was important, and I wanted to learn about it. So I kind of started from the beginning and worked my way up, and I was trying to solve a problem, as I later discovered, had intrigued many people, and it's never been solved satisfactorily. So, since I say that, you know, I didn't solve it either. But in the course of trying to do that, certain terms came up, certain functions of a sort, that began to look just very interesting to me. And I saw, well, so they were a pesky term that I couldn't get rid of. I needed to get rid of that term in order to make this formula that I wanted. But the term seemed to have a life of its own. And well, one thing led to another. I defined a certain invariant of a three-dimensional manifold, and use that to prove some what's called immersion theorems, whatever those are. This was a very handy thing. And I showed it to Chern. Said, oh, look at these results in 3 dimensions. And he looked at it and said, oh, well, we could do this in all the dimensions, because it was an area that he really knew about. Not the results that I had gotten, but the general area. So we worked together, and we came up with these results, this whole structure. In fact, that's the slides of the presentation that Chern made at the International Congress in the early 70s. It was very nice geometry. I pushed on with it, and we defined some things called differential characters, which was another chapter working with a guy named Cheeger. But the Chern-Simons invariance, about 10 years later, the physicists got a hold of it, and it seemed to be very good for what ailed them, or whatever might have ailed them. And it wasn't just string theory, as I subsequently developed. It was kind of all areas of physics, including condensed matter theory. Even some astronomers seem to want to look at those terms. That's really what's great about basic science, in this case mathematics. I mean, I didn't know any physics. It didn't occur to me that this material that Chern and I had developed would find use somewhere else altogether. This happens in basic science all the time, that one guy's discovery leads to someone else's invention and leads to another guy's machine, or whatever it is. So basic science is at the, it's the seed corn of our knowledge of the world.
What did it feel like at the time you were coming up with it? Did it feel obscure and just like a little diversion, and then 10 years later it felt special? Or
Well,
did
it never felt like a little diversion. I really liked the results. I loved the subject, but I liked it for itself. I wasn't thinking of applications. I mentioned to C.N. Yang, who was at Stony Brook at the time, who was a Nobel Prize winning physicist of great renown, I said, I've got these things, maybe they'd be useful in physics, because I knew the physicists were looking in the same places using certain mathematical structures, but he didn't bite, and I didn't know how it would be useful, so I just left it alone. But I was very pleased with the math, and then it led to another set of definitions and some math that I did with this guy Jeff Cheeger, which started as sort of a mini field, although I didn't realize it at the time, it's now called differential cohomology. And so there's a fair amount of people working in that area.
What does that make you feel? Does it become like vindication, or what I did was more useful than I thought? Or like, what do you think when it gets used 10 years later? Or by then are you divorced from it and you're like, do what you want with it, I've moved on?
Oh, it's always made me feel very good, of course, naturally. You like to think that something you did had far-reaching ramifications. It was nice, but it wasn't. I didn't go to bed dreaming about, now I've revolutionized physics, which, first of all, I didn't revolutionize physics, but did some stuff there. And, but sure, it made me feel good.